Alrighty, so in last class we talked a little bit about photoelectric effect. I just give a little bit explanation on that and then we move forward. So I told you if you have a metal here, this is a piece of metal, then there are atoms, and with those atoms there are electron bonds with certain energy. So these are the electrons here. So in some metal, these electrons are very free to move. In some metal, they are very tightly bound. So that every metal have different amount of energy with which the electron are to the atom. Yeah. So let's say this electron is bound here with 1 joule energy, right? And you shine the light here, and this light only has 0.5 joule of energy. So this energy, this light cannot eject this electron out. So the minimum amount of energy the incoming light must have more than 1 joule, right? So this is bound by the 1 joule, but you are shining with the 0.5 joule. So this light cannot eject this electron out. So this 1 joule is called work function. That 1 joule we call that is work function. So the minimum amount of energy to eject this electron out and move out from the metal surface is 1 joule, but you are shining with this surface with 0.5 joule. So this is not enough to detach this electron from the metal surface. So this 1 joule is called the work function. Suppose you shine this metal surface with 2 joule or 5 joule of energy. Let's say 2 joule of energy. So out of this 2 joule, 1 joule is used to detach this electron, just to detach this electron, and 1 joule will be used to move this electron out, like this. So you shine the surface with the radiation that has 2 joule energy, and 1 joule energy is a work function of this metal. So that is used to detach that electron from the metal surface, and remaining 1 joule of energy, incoming energy, is used to move out the electron, use the velocity to increase the velocity of the electron. So 1 joule. So this is the kinetic energy of electron with which it is moving this way. This 1 joule is just used to detach this electron from the surface. So this is called work function. This is work function, this is kinetic energy, and this is the energy of the incoming radiation. That's what I told you. Yeah? So the minimum amount of energy to detach the electron from the metal surface is called the work function of that metal. So if you measure the work function of lithium, sodium, calcium, they have very small amount of the work function. But if you measure the work function of platinum or D block elements, they have large amount of the work function. All right. So that's that. Now we start with the the lecture 2 that I posted a couple of days ago. So I'm in the lecture 2, slide number 1. So you see here, I'm drawing. I put a slide here with a figure. So this figure is all black, and there is a line around 650. So 650 nanometer. There is one line, right? And then another is somewhere near 500. So somewhere near 500, we have another line here. Somewhere near 500. 405 to between 450 to 500. So there is one line, maybe, I don't know how much is that, 486. So there is so this is 656. There is one line. In another line is there, that is 486, and there is one line at 433, and there is another line at 410 nanometer. So this is nanometer. So this is nanometer, this is nanometer, this is nanometer. All other are black there. So let's say you have a tube. You have a tube light. That tube light. You have a tube light here. So you are giving the voltage. This is plus and minus, right? This is the tube light. Just we have tube light here, and there are hydrogen atoms. So these are the hydrogen atoms. These are hydrogen atom at low pressure. These are hydrogen atom inside the tube light, the tube, right? And then you give some voltage here. So just connect to the wall or connect with the battery, and you supply some voltage here, right? And when you supply the voltage, what happened is, and put a prism here, some glass prism here. This is a glass prism. So once you turn on this electricity here, what happens is you will see four light color here. 1, 2, 3, 4 colors of light here. So this 656 is a red color here, is a red. So this is called alpha. This is alpha, and we have another one is this is called beta. This is alpha, right? This is alpha. This is called beta. This is called gamma, and this is called delta. So you see the four kinds of light, and if you measure the wavelength of those light, one has 656 nanometer length. So this is 656, and then this light here, if you measure the peak-to-peak distance, this will have 486 peak-to-peak distance, and if you measure this line's wavelength, peak-to-peak distance is 433, and if you measure the peak-to-peak distance of this light is 410 nanometer. So this is what people found by experiment. So nobody knows what is going on there. So they just put some hydrogen atoms in the tube, the glass tube, and then they supply some voltage using the battery or the electric grid, and after that it just gave the light. So it gives four kind of light, from the red to what was the one is maybe that is a violet light. So we'll see it later. So the gas gives four lines like this. So this phenomena was known from long time ago, but nobody knew what is going on here. Yeah. So like that. Now. Now I'm in the second slide. So why this phenomena happens, nobody knew at that time. So Swiss chemist, I guess, or Swiss physicist, a Swiss guy named John Balmer, J-O-N, John Balmer, was a high school chemistry teacher. So he looked these spectra. So they call these kind of things spectra, and try to explain why these lines appear once we connect the hydrogen atoms containing tube with electricity. Yeah. So he give a formula. So he try and he write a formula. So he give this formula: 1 by lambda is equals to r. He put a constant, and 1 by 2 square minus 1 by n square. So and the value of n could be 3, 4, 5, 3, 4, 5, 6. 3, 4, 5, 6. So somehow he got this formula. So lambda is the wavelength. So this number is a lambda. 656 is lambda. 486 is this one. 433 is this one. 410 is this one. And then he put the value of r here. The value of r was he put was 1.0974 10 to the power 7 meter per meter, and then one time he put 1 by 2 square minus 1 by n square. So one time he put the value 3 here. So this is a constant, and 1 by 2 square gives you 1 by 4 minus 1 by 3 square gives you 1 by 9. And put these numbers in the calculator, and he found exactly, and then calculate the lambda, and he found exactly that number, 656. Make sense? So he was just playing trial and error. Know how he did that. Yeah. Then he got this number. So he calculated the lambda, and he got this number just by putting number 3 here. 3 square is 9, right? Then in another time, he put 4 here, 4 here. So 4 square would be 16. So 1 by 2 square is 4. 1 by 4 minus 1 by 4 square is 1 by 16. And he calculated this and found the value of the lambda, and he got this number. Exactly by trial and error, he started to make some pattern there. Then another time, he put 5 here. So he put 5 here, and 5 square would be 25. 1 by 3 square is 4, 1 by 4, 1 by 25, and then he multiplied this one, and maybe just put in the calculator and found the value of the lambda, and he got 433 nanometer. Exactly those numbers are being matched with that number. Now, another time he put 6 here, as 6 square would be 36. So 1 by 2 square is 4, 1 by 6 square is 1 by 36. So put this number here, multiply it, and calculate the value of lambda, and then you got 410 nanometers. So John Balmer, about 130 years ago from today, so he was able to explain the spectra of the any atom. So from there, started the atomic structure. So before that, about 130 years ago, nobody knew where were the electrons, how they are behaving, what atoms looks like. So John Balmer, this great job explaining the spectra of hydrogen atom. So all the things today are explained by this equation. Make sense? Good. So we will continue using this equation later. So that equation is called Balmer equation. All right, so let's go to the next slide. Then I'm in the slide number 3. So why this? So Balmer gave that equation, but there is an atom, and you can connect this tube with the battery or the voltage, or you can even heat it. You don't need electricity. When you have a hydrogen atom here, just heat it, and they start to give the light. Yeah, those 4 lights that I told you previously. Now, Niels Bohr, another guy named Niels Bohr, tried to explain why this hydrogen atom on heating or on giving the electricity here, giving the 4 kinds of light here, like 646 nanometer, 423 nanometer, those alpha, beta, gamma, delta light. So he gives the structure of these atoms. So what it is, so in the center there is a nucleus. So in the center of those atoms there is a nucleus where proton and neutron are lying, and there are the circular orbit around that around that nucleus. So this is one orbit, this is another orbit, and this is another orbit. So 1, 2, 3, 4, 5. So let's make 6. So you can make infinite amount of this circle here. Yeah. So Bohr gave this model. So what he said is, okay, at the center there is a neutron and proton. So at the center there is nucleus. Nucleus. In that nucleus we have proton and neutron, proton and neutron, and hydrogen has one electron. So that electron is here at the beginning, at the first orbit at the beginning. Make sense? So there is one electron in hydrogen atom. So that the neutron and proton are in the center, and there are many circular orbits around that nucleus, and the electron is at the first orbit of that atom. Then once what Bohr's purpose is that once you give some energy, electricity or heat to this tube, what happens is that this electron is going to jump up. So it may jump up in one atom, or in another atom it may jump here, in another atom it may jump here, in another atom it may jump here, in another atom it may jump here. So there are many possibilities. There are thousands of atoms in the tube. So in one atom, maybe it got a little bit energy, so it jumped from 1 to 2. So let's say this is n is equals to 1, this orbit is n equals to 2, this orbit is equals to 3, this is 4th orbit, this is 5th orbit, this is 6th orbit. So hydrogen atom now looks like this. So Bohr said, so once you give the electricity to this tube, there are many atoms, hydrogen atom. So those electrons in those atoms pick those voltage supplied by the from the electricity, and electron jump from 1 to 2 or 1 to 3 or 1 to 4 or 1 to 5 or 1 to 6. So it jumps like that. Now after that, what happens is that once it goes to 2 or it goes to 3 to from 3 to, it jumps back to this. If electron is in the number 3, third orbit, it jumps back to 2. Make sense? When it jumps back to 2, it releases the energy, and that is seen as the light. So when the electron is third orbit, the electron jump from third to 2, and when it jumps from third to 2, it gives out the energy, and the wavelength of that energy or the light is 656 nanometer. So exactly, so 1, 2, 3, 4. So those are the line that we were talking. So 656. So this line of the energy, of this nanometer length energy of the light is produced when that electron jumps back from 3 to 2. Make sense? Simple. And then this light, what is the number of that one? So that is 486. So this is 486 nanometer light. So this is 656 nanometer light. So 486 nanometer light. So if the electron jumps back from fourth orbit, so let's say electron was here after absorbing energy, and then after a while it jumps back to the 2. So from 4 to 2, and then once it jump back from here to here, it releases energy, and that energy or the radiation has a wavelength of 486 nanometer. If the electron was here at the fifth orbit and it jumps back to the second orbit, so it gives light, and that light has how much is the 450 nanometer. So this gives a 450 nanometer wavelength light, the radiation. And if the electron has jumped to the sixth orbit in some atom, so it jumps back to the second orbit, and when electron jumps from sixth to second orbit, it gives the light with the energy of wavelength of 410 nanometers. Now the board come with this the idea of this kind of the concept, and we have the structure of the atom that we know today. Make sense? So how they found the structure of the atom? So long time ago, people put the hydrogen atom in the tube, and they used to connect this with the voltage and or battery, or they used to heat this, and once you heat this, this hydrogen atom gives the 4 kind of light. So this is the first one is the 656 nanometer light, the second one is the 486, the third one is 450, and another one 410 nanometers. So why this light appeared from the hydrogen atom on heating or on providing the voltage to this tube is explained like this. Make sense? So what the board said is, okay, so what he said is the electron travels around the nucleus in the specific permitted orbit and in no other. So he told, okay, sometimes electron is here, sometimes electron is here, sometimes electron is here, sometimes electron is here in the orbit, sometimes in the atom, the electron are moving around a certain orbit, not in others. So there is no orbit here in between 2 and 3. So this is the first orbit, this is the second orbit. So there is no another orbit here. This is the second orbit, this third orbit. There is no another orbit here. So there are already specified orbit. Yeah. So from the nucleus, okay, if it is from here to here is 1 nanometer, here to here is 2 nanometer. So just specified orbit. There is no another orbit in between them. Make sense? So now we know the structure of the atom. The electron does not radiate energy when it stays in the same orbit. So if electron is here, it does not jump back. So if it does not jump here, it doesn't release energy. As long as this electron is just rotating around the nucleus in the orbit, the electron doesn't give the radiation. Make sense? Electron give radiation only when it jumps from higher orbit to lower orbit. Or electron absorb energy if it electron absorb energy if it jumps from inner to out. It gives out the energy if it jumps from outer to inner. So Bohr said that. So when an electron moves from higher orbit to the lower orbit, it radiates the energy. So if electron jump from here to here, it gives out energy. If it jumps from here to here, also it gives out energy. So anywhere, if electron is somewhere here and it falls back, so if that is the case, it is immediately giving the energy and we can see the light. Yeah. And if electron if electron was here at the beginning, if it absorbs some energy, it is going to jump up like this. If electron was here, it gives some energy to this one, and then it picks that energy and it jumps out. So if the electron gets the energy from outer source, it jumps up in higher orbit. But if the electron jumps down in the inner orbit, it releases the energy, and we see the energy. Make sense? So if the electron jump from here to here, we call it absorption spectra. If electron jump from outer to inner, then we call the emission spectra, because either light is being absorbed or light is being released. If it is absorbing the electron, if the electron is absorbing the light, so we call absorption spectra. So it absorbs and goes out in the higher orbit. If the electron is releasing jumping back to the lower orbit from outer orbit, it emits the light. So we call the emission spectra. Yeah. So these are called emission spectra of hydrogen atom. So this is the atomic structure of the given by Niels Bohr. And so this is the atom. So this is the nucleus, and this is the orbit, n equals to 1, n equals to 2, like this. So if the electron is here, so this has a negative charge, and this is a nucleus. In nucleus there is a proton. This has a plus charge. So this is negative charge. This is positive charge. So why this electron just keep rotating in the certain orbit is because the electron is being pulled by this positive charge. Make sense? And then this electron is moving around, so this electron just wants to go out like this. So that is called centrifugal force. So electron want to go, when it is traveling, it just want to go out from detaching like this. But there is a plus sign, the positive force here. This is negative charge, this is positive charge. So this is being attracted this way, like this. And then this electron is, when moving, it just tries to go out. So that going out force and this pulling in force become equal, so that this electron keeps moving in the orbit. So that's he said that. So if you are running in the circular path, you just try to go out of the track, but you need to put effort to turn around, right? So just like that. So this, when you are running in the circular path, you just try to throw your body out of this track, but somehow you need to put some effort to remain in this track, just like that. So this positive charge proton in the nucleus pulling the electron toward it, and this electron, since it is moving, it has some centrifugal force, and it is trying to go out of the orbit. So those two forces become equal, and it is always remaining in that orbit. So the Bohr proposed those 4 points there. Make sense? So from this point, we started to know how the atoms look like. Yeah. Good. So now, in the slide, so how much energy is with these electrons? So let's calculate the energy of the electron. So here, this is the how much energy an electron has. So this is a atom. So you have a proton, neutron here. There is an electron in the first orbit, n equals to 1, or the electron may be in here, n equals to 2. So electron may be anywhere. So maybe n equals to 3. Electron may be in here. So how much energy this electron has, or how much energy this electron has? How much energy this electron has? So we derive an equation, and that equation is minus RHC by n square. So this is how they calculate the energy of one electron. Make sense? So E is equals to RCS. So energy. So what is the value of R? The value of R is 2.16 10 to the power minus 8, 10 to the power minus 18, 18, that's R. Actually, that's not. R is, sorry, that's not true. So R is 1.0974 10 to the power 7 R, and then H, we have H is 6.62 10 to the power minus 34, that's the Planck's constant, and you have the velocity of light. The velocity of light is 3 multiplied by 10 to the power 8 meter per second. So you have this RHC value, and then divide by n square. So n means where is the electron? If it is a first, so put 1 here, 1 square is 1. If the electron is in second orbit, put 2 here, 2 square is 4. If electron is in third orbit, put 3 here, 3 square equals to 9, and then calculate the energy. So how much energy it has? So if you multiply this, and this number, you get 2.16, 2.16 10 to the power, 2.16 10 to the power minus 18. 18 joule divided by n square. So it's very simple now. So why they put minus sign here? Because they think that, okay, it makes more sense if we put the negative sign in for the electron energy. So they just give a negative sign for the energy. Yeah. So like this. So how much energy if you have a electron in the first orbit? Put n equals to 1 here. 1 square is 1. If you divide this number by 1, that number is 2.16 10 to the power minus 18 negative. So that much energy in the first orbit. So if you if the electron is second orbit, so put 2 here. 2 square is 4. So 2.16 10 to the power minus 18 by 4 would give you 0.54 10 to the power minus 18 here. And if you put how much energy this electron has in third orbit, so if the electron is in third orbit, put 3 here, 3 square is 9. So 2.16 10 to the power minus 18 by 3 square is 9. So when you put this number in the calculator, you will get 0.24 10 to the power minus 18. Yeah. So how much energy it will have if it is in the fourth orbit? So if the electron is in the fourth orbit, put 4 here. So this number is always same. So C multiply is always same. So you don't have to multiply every time. So this number is same. N square is equals to 4 square equals to 16, and divide this number by 16, and how much you get with the 0.135? You get 0.135 10 to the power minus 18 joule. So that's how they calculate the energy of the electron. Make sense? So now. So I am just trying to draw a neat atom again here. 2, 3, 4, right? Or so 1, 2, 3, 4. I could do 5, 6, whatever, right? So this is n is equal to the first orbit. Electron is here in the first orbit. Electron is in the second. Sometime it is in the second orbit. It is sometime in the third orbit. Sometime in the fourth orbit, and sometime in the fifth orbit, and in sometime in the sixth orbit, seventh, eighth, ninth, infinite number of orbits are there. Yeah. So how much energy? So I just calculated how much energy in the first orbit has. So if n is equals to 1, that electron has the energy of 2.16. If n is equals to 1, energy 1 will be. Let's do from higher orbit. So n is equals to 4. I start with the n is equal to 4 because I calculate here. So if the electron is in the fourth orbit, how much energy I have? Let's say that is E4. So I have electron in the fourth orbit. How much energy with this electron? So I calculated that is minus 0.13 10 to the power minus 18. Then how much energy of that electron in third orbit? So that would be 0.24 minus 0.24 10 to the power minus 18 joule. If I have electron in second orbit, how much energy that have? So that will be So that's E2. So that will be minus 0.54 10 to the power minus 18 joule. And then if I have the electron in the first orbit here, so the energy will be minus 2.16 10 to the power minus 18 joule. Yeah. So now what I want to emphasize here is one thing. So if you look here, this number looks very big, 2.16, right? But this is not a big number. This is a very small number. Why it is a small number? Because it's a negative sign, right? So is negative 2 is big number or negative 0.1 is big number? Negative 0.1 is big number. Negative is very, very small number, right? Because this is negative number and this negative 2. So like this. So which number is a big number here? So this is a number line, this is 0. So 1, 2, this is plus 1, this is plus 2, this is plus 3. Now this is minus 1, this is minus 2, this is minus 3. So so 0 is a very large number. If you consider the negative number, compare the negative and positive number, 0 is a very large number compared to minus 1, right? So minus 1 is very large number compared to minus 2. Minus 2 is very large number compared to minus 3. So this number is very large number. So just looking here, 0.13, you may say, oh, this is a very small number. No, since there is a negative sign, so this is very large number, very large. This is large number. This is large number. And this one, minus 2.16 is small, it's very small number, so it's small. You see that? So in the first orbit, the energy of the electron is very, very small. In the second orbit, the energy of the electron is a little bigger. In the third orbit, more big. In the fourth orbit, energy is higher. In the fifth orbit, energy is even higher. So this number is very large. So if you go E5 here, you will get very small negative number here. So that is a big number. So this number is big. So what I'm trying to say is this is a big number. It's a big number because small negative number is a very big number, and this is a little bit smaller. This is more smaller, and this is the smallest. So smallest energy is in the first orbit. So if the electron is in the first orbit, it has a very, very small amount of energy, and we call this is a ground state. Yeah. So when electron is in the first orbit, it is called the ground state. So if the electron is here, we call it the ground state. Why? Because it has not left the ground. So it's still in the ground. So this is the lowest place where it can be, right? Where I am standing is in the ground now. I have not left the ground. So this is the ground state. So if I jump from first floor to second floor, I call that is the excited state. I am excited from first orbit to second orbit. Make sense? So it's just the word meaning is sufficient to describe the thing. So if the electron is in the first orbit, that is called the ground state. If the electron has left the first orbit and go to the second orbit, third orbit, or fourth orbit, or fifth orbit, sixth orbit, that's called the excited state. So the energy is always higher in the excited state. Make sense? So remember that this number is a very big number. This number is very small number. Minus 2.16 is very small number. Minus 0.13 is very big number. So energy is higher in the so when I was in the undergraduate or under the class I was studying, I was always confused. Which one is? Oh, the book says this number is a large number. This has a high energy here. How is the high energy? This is very small number here, right? 0.13. But since there is a negative sign they give, so that negative sign makes this number a big number. Make sense? So don't get confused there. So like that. So now what? Now this is fifth orbit here. I have fifth orbit. Another orbit is sixth orbit here. So n is equal to 5, n is equal to 6, n is equal to 7. You have many orbits there. Now, if the electron jump from 3 to 2, so if the electron is jumping from 3 to 2, you get one light. If the electron is jumping from 4 to 2, you get another light. If the electron is jumping from 5 to 2, you get another light. And if the electron is jumping from 6 to 2, you get another those 4 lights. So those 4 lights that we see already, in this 1, 2, 3, 4. So this was 656 nanometer alpha line, and this was a 410 nanometer delta line, right? So we have that. So 410 and 656, 486, 656, 486, 486, 410, and this is alpha, this is beta, this is the gamma is how much? The gamma is 433, 433, this is gamma, this is delta. So four kind of the light. So these things we can see with our eyes. So if the electron jump from third to 2, it gives third to 2. So third to 2 is this one, this light. So we can see with our eyes. If the electron jump from 4 to 2, this gives this wavelength light. We can see with our eyes. And if the electron jump from 5th to 2, we can see with our eyes. That's a 433. If the electron jump from 6 to 2, we can see with our eyes. That's a 410 nanometer. So this light produced by hydrogen atom, we can see with our eyes, and this is called the Balmer series. So this four kind of the light is called Balmer series, because it is explained by the Balmer equation. Make sense? So Balmer series is, there are four kind of the light we can see with our eyes when the electron jump from third to 2, fourth to 2, fifth to 2, or sixth orbit to 2. All those light we can see with our eyes, and those four lights are called Balmer series or Balmer's lines. Make sense? Good. So these are the Balmer series or Balmer light, Balmer series. So these lights 1, 2, 3, 4. So this is red light. So this is red light. This is red. This is red, and then this is toward the violet. So you can see this kind of the light. Yeah. So this is Balmer series. How about if electron can jump from here to here? Let's say electron jump from 2 to 1, or 3 to 1, 4 to 1, 5 to 1, 6 to 1. So these are the, if the electrons are there and they jump to first orbit like this, they are producing the light, but our eyes cannot see them. Make sense? Good. So there are the light, and if they are jumping to the first line, they are called the Lyman series. So this another guy, maybe Lyman, he just studied those, but he could not see with eyes, but he built the instrument, and he looked those lights, and he saw those lights through the instrument, and they are called the Lyman series. So all the electron jumping from second, third, fourth, fifth, sixth to the first orbit, they are giving the light of different wavelength. Our eyes cannot see them, and those lights are called the Lyman series. Yeah. I'm in the slide number 4. How about they jump to the third orbit? So let's say light, the electron is 1, 2. Now let's say this is n equals to 3. So we have many orbits here. So electron is jumping from 4th to 3, and 5th to 3, and 6 to 3, 7 to 3. So electron is jumping from outside to the third orbit, and those light, the electron is releasing a lot of energies. There are many kind of the wavelength or the frequency, having frequency of different frequency and wavelength and energy, and those also cannot be seen. And this are studied by Paskin, a scientist named Paskin, and this is called Paskin series of light, PASCHEN Paskin series. Make sense? So if the electron jumping from 3rd to 2, 4th to 2, 5th to 2, 6th to 2, we can see with our eyes those lights. But if the electron is jumping from 2nd to 1, 3rd to 1, 4th to 1, 5th to 1, 6th to 1, it is giving the light, but we cannot see with our eyes. Yeah. So they are called the Lyman series. And then if the electron is jumping from 4th to 3, 5th to 3, 6 to 3, or 7 to 3, so we also cannot see those kind of the light, and they are called the Paskin series. So they are in the infrared region. They are like the hot kind of the light. Yeah. So Lyman. So these are the Lyman series. So we can see this. This comes in the ultraviolet region toward this side. So toward here, ultraviolet. So it becomes this way here, and then this one is we find the infrared region here. So these are the infrared region, these are the ultraviolet region, and this is the visible region. So visible region is if electron jump from third to 2, fourth to 2, fifth to 2, sixth to 2, and this one infrared 4 to 3, 5 to 3, 6 to 3, 7 to 3. So these are in the infrared region. We can see our eyes. These light are produced in the ultraviolet region if the electron jump from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, like that. Yeah. So only these can be seen. This one and this one cannot be seen with our eyes. We need an instrument. Yeah. Makes sense? So only the Balmer series or the Balmer those 4 lines we can see with our eyes. Good. So this is important. Now 2, 3. Now here this one in the slide number 5, I already told you which number is a big number, right? So let's say this is a nucleus. This is a nucleus here. Nucleus. Electron never be in the nucleus. Electron never jump to the nucleus. Yeah. You never find electron in the nucleus. And this is the first orbit here. This is the second orbit. This is n equals to 1. This is n equals to 2. This is n equals to 3. This is n equals to 4. Then this is n equals to 5. This is n equals to 6. So these are the orbits, exactly like this. N equals to 1, 2, 3, 4, 5, 6, like this. So I can just write this, not if I don't write, so the atomic structure like this, I can write the energy level like this. So how much energy in with the electron that if electron is in the first orbit? I already told you E1 is equals to minus RHC divided by n square. So multiply RH and C, you will get how much you will get is 2.18 minus 2.18 10 to the power minus 18 here, and put n equals to 1. 1 square is 1, right? And you get the energy of this electron. Here, put RHC value, again 2.18 10 to the power minus 18, 2 square would be 4, right? And then calculate that, you will get the energy of this electron. Energy of this electron, calculate like this. So if you are calculating energy of the sixth, if the electron is in the sixth orbit, how much energy that would have? Minus RHC by RHC would be 2.18 10 to the power minus 18, and then n square, n is 6, n square would be 36. Put 6 here, divide 2.18 by 36, and then that means you will have in the energy in that sixth orbit. Make sense? It's pretty easy, right? And then I told you this number is a very large number. Although on calculation you see very small number, this is a very large number here. Very large energy, big number. You will see small there, but minus the small number is the biggest number, right? And then this number is the smallest number. Here you will see minus 2.18 10 to the power minus 18 joule is the smallest energy. So in equal to 1, we have smallest energy. As you go up, the bigger. But you get confused with the negative number there, yeah? So I am always confused with that negative number. Why they put in negative instead, making our life a little bit harder. But if I had done this experiment, I would just give the positive number there. Good. So like this. So this is the second slide. The fifth slide. Now in the sixth slide, let's go to the sixth slide. And how do people do experiment these days? So it's very simple. So let's say you have some element. I have some mercury vapor, right? I have mercury vapor, or I have iron vapor. So I just put those vapor. Let's say I have a mercury vapor, so I put those mercury vapor here. This is a mercury vapor here, right? Or iron vapor, or you can get copper vapor. It doesn't matter what element. Just put some atoms there in the vapor form, and just give some light here. So, meaning that you connect that the tube to the voltage or the heat this atom. You can heat it, or you can connect this with the high voltage battery. And then what you do is basically you put a prism here. So you put a prism here. So you put a prism here, like a prism, right? You prism, and then send this light here like this, and So the light is coming here, and you will see the prism will separate your light in different wavelengths here. So maybe this is violet, this is red, and when you plot those in the series here, you could see different line like this. Like this. So 1, 2, 3, 4, 5. So this this line here, and this is this line here. So if it is a if in one experiment, if you take the, let's say, the iron here, maybe or mercury here, mercury vapor, no matter where you do this experiment, this number always comes in the same place. So do I have here? So let's say I have a mercury here. So mercury, if I do the mercury, it's the mercury vapor. So and then I put here mercury vapor always this. So you look at the 7 sides. So you will see 2 line here. You will see another line here, and you will see another 2 line here, and then you will see 1 line here, and then you will see 2 line here. So something like this. So this is no matter where you do the experiment or where you do the experiment, this line always come in the same place. So that's how people identify the element. So how do people know that, okay, our sun has hydrogen? So they do the experiment on Earth, and they look this spectrum, and hydrogen behaves certain way like this. And they turn their telescope toward the sun, and they observe the light coming from there, and that exactly behave is how our experiment is going in Earth, right? So they say that, okay, my spectra on Earth and my spectra on the sun looks exactly same, so the sun must have hydrogen here. Make sense? Or sometimes people look the star, and then they say, okay, in Earth they have a spectra of iron, so they have already done spectra experiment of the iron vapor. So they see 1, 2, 3, 4 light at certain wavelength. So maybe this is 200, this is 100, so something like that. So this is this one, and they turn their telescope toward the one star, and when they put that light, exactly that light also giving us this four lines. So this, oh, okay. So the light coming from the star is resembling my iron spectra on Earth. So that star must have the iron content. Make sense? So that's how we identify the element. So you go to the lab, somebody gives you some vapor, and then what is this element? So just run the experiment, you get this 4 line here. Okay, then you got this one. Now go to the database in the computer or the government website, and which does it resembles with, and this resembles with your spectra, resemble with the iron spectra that people have already done it. So the element people give you is must be the iron. Make sense? So we just compare our spectra with the standard spectra people have already studied, and we identify the element. Good? So this is called image. It's a very important tool. Spectroscopy is a very important tool. You do your experiment, get a spectra, and go to the website or the database and pull some spectra and look where with which one your spectra is resembling, and you found that, okay, that spectra resemble with that spectra people have said, so this is that element. Yeah, so this is called the spectroscopy. It's a very important tool in characterization of the material. Doesn't matter whether it is a biology, it's a chemistry, physics, doesn't matter which subject is, we do the same thing. Alrighty, so I think we studied a lot, so hopefully you understood something. So we will continue from actually there is not much thing in 4th and 5th slide, and we will do a couple of calculations, and we start the next lecture. So I posted the 3rd lecture in the Canvas study night. So next week we will do this. Make sense? All right, everyone. So I'm going to stop it.